Hi and welcome. My name's Andrew Czapkowski. I'm the lead developer on the ArcGIS API for Python. And what we're going to talk about is getting to know Pandas and the Spatial Enabled DataFrame. So let's get started. So the first question is what is Pandas? And Pandas is a package that provides fast and flexible expressive data structure, and it makes working with relational or labeled data easy and intuitive. And this makes the data kind of feel like an Excel spreadsheet, but we're doing it all through code. And the question is why should we use Pandas? Well, Pandas handles missing data very easily, where a lot of structures do not, especially within Python. It's size mutable, which means it can change. It has automatic and explicit data assignment, and it has these very powerful group by functions, just to name a few. Some other reasons is that it has really powerful slicing, and it has great indexing, so it just doesn't have to be an integer. It can be multi-index, so you could have a datetime and an integer. You could just use a datetime, you could use a string, so it's really powerful there. It has intuitive merging and joining, and it has the ability to reshape our data in just a few lines of code. So let's get started, and it first starts by getting the library imported. So we're going to import pandas as PD. Let's go ahead and run that. Next, we're going to go ahead, because we're in Jupyter Notebooks, I'm going to do %matplotlib inline, and this is a magic function that's going to allow me to draw my charts on the map, which we're going to get to later. Now that we have that, let's talk about the first type of data structure we have, and this one's called a series. And a series is a one-dimensional labeled array, and it can hold any data type, so it just doesn't have to be an integer, it can be anything. We're going to do import numpy as np now to create some fake data, and we're going to get random data. And we're going to go ahead and create our series. So we're going to do pd.series. This is going to create that one-dimensional array that we have, the class series. And we're going to pass in our array structure. This is going to create an index on the fly. Notice that on the left, 0 through 4, our 5 entries that we created above, the values, in this case float. And then it automatically determined what the data type was. If I were to put just integers in there, so numbers without decimals, it would have determined that the data type was integer, and so on. And same with datetime objects. Now, going from the one-dimensional column, we have the two-dimensional view, and this is where you get that Excel spreadsheet example. And this is our data frame, and it's made up of both columns and rows. And this data structure is a labeled data structure, so think of it in Excel, your first row with your column names would be the first row, and those are your labels. And then all the data comes underneath that. And it could be any data type as you have. So let's go ahead and let's create our first data frame. So we're going to go ahead and we're going to create our data frame by providing a list of lists. This is just one way of the multiple ways you can go ahead and create data. I'm also going to assign it some field names, though this is optional, you don't have to do that. So I'm going to do df equals pd.dataframe, pass in my data, pass in my columns with the names, and get my data out. We can see that we have our field 1, 2, 3 with our associated values underneath it, just like we would expect. So now, we don't always want to create data from nothing, so we're going to use one of the provided data ingesters to read some information in. We're going to do df equals pd.readCSV, and then we're going to pass in a path to our CSV file. Now we've ingested a CSV file. There are a whole host of data ingesters if you just do that you can use within Pandas, and CSV is just one of them. Out of the box, it supports multiple types, from reading pickle files to CSVs to even Feather and HDF formats. We can go ahead and peek at our data, which is going to allow us to sort of see a small portion of our information by using both heads and tails. df.head will show the top 5 rows within our data set. df.tail, on the other hand, looks at the bottom 5. Also, it's good to note that like most Python array objects, it starts with index 0, not 1. We can do slicing on the data frame as a whole, just like we would an array within Python. So we have our start, our stop, and the step size. Go ahead and show that, and we get the rows. See, we have 23, 26, and 29. To get a good sense of your data, Pandas has a lot of built-in functions that allow you to understand, especially numerical data, very easily. And one of them is called df.describe. This will take the numerical columns in general, and it will provide some basic information. So it'll provide you with a count of the amount of non-null records, give you the mean, the standard deviation, min, max, and the quartile breakdowns. When data is loaded in order, it's good practice to shuffle it up before doing any sampling, especially for statistical analysis. To do that, we do df equals, so we're going to reassign our original data frame back, and then we're going to do df.samples. That'll mix it up. And if we want to drop the original index so we don't know the original order, we're going to reset the index and drop it, setting that equal to true. And then I'm going to go ahead, I'm going to df.head, and that'll show the first 5 records. And we can see that records, the first record here is different than our original first record up here. So our data's been mixed up just like a deck of cards would. So we looked at the data frame as a whole, but we can look at individual pieces of the data frame as well, such as column names. So we just take our data frame object, do .columns, and it returns back an array-like object, in this case called an index, with a list of all our columns within our data set. We can do df.dtypes, and what dtypes is going to allow us to do is it's going to say, hey, I have all these pieces of information in here. What is data type of each one-dimensional column or series? Notice that name comes back as object, not string. So in a future release of Pandas, they will be changing that to actually return back string. We can access data multiple ways, but the most general way is to use the iloc, which is the index locator, or LOC, which is or the lock method, and passing in the index that you need to get there. So let's say we want to get the 8th row, so we can do df.iloc 7, and we put 7 in for the 8th row because remember we start at zero-based indexing. We can select individual columns and only see parts of our data frame. And this is sort of analogous if you do anything with databases, like creating a database view. So here I only want name and sepal length, and then I'm going to show the first 5 records. I can also access individual information on a series. So I'm going to do df.name.iloc and then get back information from that single row. We can slice using iloc as well, and here we can do start. We provide a start index, stop index, and step size. Now, when we just wanted an individual location, we just did iloc of our start index, and then everything else is ignored. So, but here we can say I want start and stop 1 through 16, do 3 steps, just like we did before with the whole data frame. Another really fascinating thing that you can do with Pandas data frames is called method chaining, and this is going to allow us to call one method after the other. So we're going to do variable assignment data frame. So we're going to rewrite over our original data frame, and we're going to rename all our columns to lowercase by doing .rename columns equals str, which is string .lower. So we're going to pass that function in, and then we're going to use the df.assign, which is going to allow us to work with data within the data frame itself. Pass in a lambda function, lambda x equals x, and then we want to access the column name. Notice that we had to change name to lowercase because the rename already occurred. So now all the column names are now lowercase. And then do .string.lower, which is going to lowercase all the values within our column. And then we're going to print out and display the first 5 rows. And we can see that we changed the column names and the string values within name are all lowercase. Something that's pretty neat within Pandas is the ability to work with datetime objects. It handles them very well. Here's a case where we have data. It's all integer values, but they represent date times and they're spread across multiple columns. We can convert that really easily. So let's do df.DataFrame, and we're going to assign the values in. So we're going to create a new data frame. Now we just have month, day, year, and hour. And here's the values associated for each one. Let's say you want to then create a new series and make that a datetime data type. So we do pd pandas dot to datetime and pass in our whole data frame. Pandas looks at all that and recognizes the column names and is able to create our datetime object for us. So when we go ahead and do that, we can see that we have our new column with our types in here. And notice it lined everything appropriately. And then we can look at the datetime objects and see that we have datetime N64 for the datetimes. Datetimes, datetime 64. We can set datetimes as an index. So if we have anything, if you're working with time series data, we can go ahead and we can assign this datetime that we had here as our index instead of being our numerical value. So let's go ahead and look at that. So we're going to do the same concept we had before. We're going to use that pandas.toDatetime, pass in the columns we want to be in our index, and then we can go ahead and query based on that index and get that individual row. So here we're using lock instead of iLock because we're using a datetime object, and we get back our individual row based on that date. So if you have time series data and you need to pull out for individual times to do analysis, this is one way you can do that. Let's go ahead and look at categorical data. And they're sort of like domain values on a feature class. These are fixed number values. When you have a fixed number of values within an individual series, you don't need to keep each of those values in the series. You can use a small integer value because your memory footprint will be small and Pandas will handle all those lookups for you. So we're going to go ahead and we're going to create some random integers from 1 to 100. And we're going to go ahead and we want to group those values. So what we're going to do is we're going to go and we're going to create our categorical data and create these groups for each one based on these ranges. And we're just going to look at the first 5 rows. Using pd.cut, we can pass in our values, the range, and then the labels that we want. And we can display it, and it'll automatically create these group categories for us. We can also, for data that doesn't, that we pull in, we're going to take an example of looking at drinks database, drinks layer that deals with alcohol consumption around the world. So we saw before consuming Pandas, consuming CSV files locally, but you can also pass in a URL. And then as information is being passed in there, we can assign data types. So for continent, we can say that this is a categorical value because there's a limited set. There's a limited number of continents in the world, and we know what they are. So that's a good case for having a category for that. So let's go ahead and do that. We can see that we get our index value for each continent displayed here. Now let's say we don't know what our data is when it comes in. So we're going to take that same drinks data set and load it in. And now we look at it and we go, oh, okay, continent is here. We know that we need to, I want to make that a category. So post load, we can do drinks.asType and assign the various values of how we want these values to be represented. So right now we have beer servings and spirit servings as integers, but we want those to be floats, and we want our continent to be categories. So we can just do, we can set our asTypes function, assign it back to drinks, our data frame, and then look at the D types. And we can see that they changed from the spirits were originally integers and now they're floats. and then continents was a string, and now it's categories. So there's general statistics operations that we can do, and Pandas provides both basic and advanced statistics. One area that basically should be performed in mass, especially on large data sets, is aggregation. So let's go ahead and take a look at this. We can do aggregations on group data, data frames, and series, and I'm going to show an example of each. Here we have our drinks data set that we've been working with, and we're going to look at beer servings for our series value. We're going to do series.ag and then provide the ones that we want to do. And the reason we do it this way instead of doing each individual aggregation is because we don't want to walk our data multiple times, especially on large data sets. And when I'm talking about large data sets, I'm talking about data sets that have maybe millions of rows. So we want to do it once and walk the data once and be done with it. So here we get our mean, min, and max all in one go, one pass. We can do the same thing on the data frame. So we take our data frame as a whole, and this is going to give us the mean, min, and max for our numerical columns. And also notice that for countries, we got back information too. And that's because string data has a min value, which is A, and a max value, which is Z. So min and max are valid on string data, but mean comes back as NaN, which means not a number. So, or null, if you want to consider it that way. So our data doesn't get returned there. Just something to be aware of. We can group by, let's say we want to know the aggregations by continent. So we can take that categorical data that we had and perform a group by operation on it. So we're going to do DataFrame.groupBy, our value, take the column that we want, and then perform those same aggregations, but we'll get back a different result. Notice our index now is the continent, and then we have our mean, min, and max for each continent. Pandas provides a visualization that's pretty rich and complete, and it's built on top of matplotlib. So let's go ahead and just do a simple plot. Here we're going to create some random data, and we have two columns, and we're going to use the time series function. We're going to do CumSum, and we're going to go ahead and we can just show the series, and we get this sort of jagged plot going through B. Another thing we can, so that's a simple graph, but the other thing that we can do is we can look at an advanced sample. So what we're going to do is we're going to take some random data and we're going to hex bin them. And this is going to create a nice visualization of our data from here. So these two examples are basically to show you that you can do something simple and something complex and still have the ability to visualize your data accordingly without having to go out to another third-party library. And all this, now that we've seen how it works, leads to something that we're going to use in the next demo on part 2. And this has to do with data wrangling. A lot of functionality within Pandas is to do data wrangling or to modify and scrub your data. So we're going to use this concept that comes from R, and it's called tidy data. And what we're going to do is we need to make the data that we have to fit our needs. And we're going to use data wrangling is going to be the process of doing this, and you might have heard that term before. And our goal here is to have three things. Each variable is going to form a column. Each observation is going to form a row. Each type of observational unit is going to form our table, which is our data frame. Okay, so let's go on to part 2 of data wrangling. So I'm just going to recall, so it's here, I just want to recall that our data wrangling rules is that each variable is going to form a column, each observational forms a row, and each type of observational unit is going to form our table or data frame. So let's start by importing our data. I'm going to import OS and Pandas as PD, like we did before. And we're going to take data from basketballreference.com, and we're going to look at some games that occurred in 2016. I'm going to go ahead and pull that data down. And what I was able to do here is I went out to the internet, to this website, and I looked for an HTML table on the site. It then scraped it for me. I was able to pull the table in, and then I dumped it to a CSV file to save it. So next time I come to do it, I don't have to re-download it. And then I displayed the first 5 rows. So we saw, I talked about how Pandas can read a lot of information, but we all now here's another action, a very powerful action, is this read from HTML. If you think of all the data that's out there on the internet, not all of it's readily available as CSV files or some other friendly format. So this is where data wrangling really starts to come in. So now that we have our data, we're going to clean up our column names. And we're going to leverage method chaining. We're going to remove some unwanted information. I want to normalize the column names. I want to drop data that just has a lot of missing values. I'm going to do some assignments to clean up some data. Set a new index and to do some, and then rename it. Let's see how we can do this all through method chaining. So my column names, I'm going to define them as key value pairs in a dictionary. So I'm going to convert, example, capital date to date, start time space, parentheses, ET to start, and just get rid of some of the unwanted things that I don't want. So I have my games data set. So I'm going to take my games and then do the dot rename. In this, now before when we were looking at that, you recall that we passed in the function str.lower, which is the string operation for lower. In this case, I'm passing in that dictionary. So for the first rename, I'm going in for the columns and saying, if this name exists, change it to that. The second rename that I'm going to do here is going to make sure that anything I didn't change before is lowercase to match the ones I did with the original column. I'm going to drop rows that are columns that have a threshold of 4 of null values. Then here's a new thing that we haven't seen before. I'm going to make that copy of our data set and only pull in the columns that I want. So here we have data, away team, away points, home team, home points. I'm going to do an assignment on the date to convert the value from a string to the datetime object. Set my index to the date, rename, and sort, and then look at the first 5 rows after I've done all that. So here's our results. So notice we get we don't just have a single integer based column or a datetime. We have a multi-column index. Now we have our away team, which is the Detroit Pistons, the away points, home team, Atlanta Hawks, and 94 points. And I did all this to answer a question. And I wanted to say, how many days of rest did each team get between each game? And the question we have to ask ourselves, if we go back to those original rules, is my data set tidy? And since our observation for this case would be that a team comma game pair, we don't have that yet. So we need to go ahead and figure that out. So we're going to take advantage of pd.melt. And if you never, in Jupyter notebooks, a really interesting thing that you can do is for any function that you don't know exactly how to use, or you just do the function ? And it'll bring up help for us. And then we can see that unipivot is a data frame from a long format optional leaving identifier set, and then it says this function is useful to massage data sets in a format where one or more columns are identifier variables like we have. So we're going to use that pd.melt to get our data set tidy like we had before. So now that you know how to look up help, and we can go ahead and do this. So to get our observational pair, we're going to use pd.melt, combine it together, and let's see how our tidy data set is now shown. Here we go. So now we can ask ourselves again, is it tidy? So it's going to meet our rules that we defined before. So each variable is in a column now. Each observational is in its own row. Each observation is its own row, and each type of observation forms our table which is our data frame. Now, when we think of doing asking questions, a lot of times we ask ourselves questions in the form that we would understand as humans, but we need to answer questions in the form of how a computer thinks, or how can we interpret it that way. So the question is how many days of rest between games we need to change it to the date of today's game minus the date of the previous game minus 1 to get it in the form that the computer can understand. So we can go ahead and do that. So we can just do tidy, create a new column rest, use our method chaining. We're going to go ahead and do tidy.sort values on the date. We're going to group by team and create that difference that we had before. I'm going to drop some NA values and display the top 5 rows. And here we can see for the first 5 rows, we have the days rest for each team. So we can see the Chicago Bulls had 0 days rest on this game. You can go ahead and then visualize this. In this case, I'm going to use Seaborn. Going to plot it out, and we can see some of the games, the days rest for each game. And then you could take this information and further pass it on and look and to see if maybe there's a association between points scored and days rest. So now we're going to move on to part 3. And that's working. Let's get a little spatial. So we've seen Pandas, and we've seen the how it makes us have the ability to work with tabular data very easily. Now let's take these concepts that we've learned from the first part and put them in the context of doing spatial operations. So we introduced a few versions ago the Spatially Enabled DataFrame. And what the Spatially Enabled DataFrame is Pandas DataFrame that's built on top of Pandas, and it has what are called accessors. And accessors are these namespaces that we inject when you import the library into Pandas. And this is the preferred way of doing design on data frames. So our 2 namespaces that we added are spatial and geom. And we also created a custom date type called geometry. And it provides a different geospatial experience than you're probably used to when you work within ArcGIS Pro or ArcMap or any other product out there. And the data is in memory. It tends to be very fast. You have on-the-fly indexing, and it's multi-platform, which is one of its biggest features, is that this data frame and the Python API in general can work on any operating system, Linux, Mac, Windows, the big 3. So we have these custom namespaces, and they exist in 2 unique areas. The geom exists on a series, and specifically it exists on the geometry series itself. By default, the geometry name is shape. So you could say something like DataFrame shape, so we're going to get that 1 column. And then you do .geom, and that gives you access into these custom spatial functions that will operate on the geometry object. And then you could do .area, and it would give you the area for each, assuming you had a polygon, it would give you the area for each polygon, and it will return that back as a series for each row. Series with each row being an entry for that geometry. And then spatial works on the data frame, and these are the operations that are going to exist on the data set as a whole. We can do things like df.spatial.project as and reproject on the fly our data frame from whatever current coordinate system you have to, in this case, 4326, which is WGS 1984. Some other benefits, like I said before, it's cross-platform. We support multiple geometry engines, and we're going to be enhancing that in the future as well. And you can read, write data using a whole host of Python packages. So we support Fiona, PyShape, which is shapefile, and ArcPy. So let's get started now that you know some of the preliminaries. The easiest way to import it, if you just want to import the accessor component of the Python ArcGIS API for Python, you would do, like before, we do import pandas as PD. And then we could do from ArcGIS.features, import geoaccessor and geoseries accessor. When this runs, which we're going to run right now, it's going to inject those namespaces or register those namespaces with pandas, and now we're able to use them on the series and data frame as a whole. We have a lot of I/O operations, just like you can consume information using the to and write information using the to and from methods based on the default spatially default data frame. You can do those I/O operations on from the spatial namespace on the ones of the whole. So some of the things we consume, some of the consumption methods that we have is, let's say you have a feature layer service and you want to bring it into a Pandas data frame. You can do pd.dataframe.spatial and then do from layer, and this will create a spatially enabled data frame for you. You can consume from feature classes. So this includes your shape files, your file geodatabases, whatever. We can read information from a CSV, and if it has a lat long column, you can then convert it. So we pull in our CSV information from the USGS website, the feed for the all hours CSV. It's going to load that into here. And then we can create our third spatially enabled data frame by doing pd.dataframe.spatial from xy. Pass in our regular data frame, supply the x and y columns, and then we can specify the spatial reference. So this means that you're not tied to just having WGS 1984. You can do it in any coordinate system that has a WKID. So that's consumption. We can persist data in a few ways. We can write out to tables, feature classes, and services in general. The easiest way to push information to your enterprise or ArcGIS Online would be to do gis.content.import data, set your data frame to the DF object, and give it a title. This will go ahead and publish a service and save your information up on your enterprise. If you want to save it local, we have a to feature class function, and you provide a location. The location includes the full path to where it's being saved, plus the feature class name. So let's recall that our series is a one-dimensional array of values. Now let's explicitly look at how we can work with our data and the shapefile series. So we have our spatially enabled data frame that we're going to load in. So we do pd.dataframe.spatial from feature class, and we import our data. In this case, it's a file geodatabase that I have stored locally. Now I'm going to do sdf.shape equals .head and get the first 5 rows, and we can see it comes back as Esri JSON. We can go ahead and access properties on this. So in this case, I want to get the centroid of those polygons. So I just do sdf.shape.geom, and it returns back an array of xy values in the coordinate system that your data is in. We can do calculations on this. So let's say I have my geometry and I want to get the area. Because I'm going to project it, I'm going to use planar, and I want to get my area in acres, and then I want to sum it all up. So I'm going to do sdf.shape.geom.getArea, pass in my variables, and it's going to, and then at the end, for each of the values that come back from that series, they're going to get added together by using the sum method, and we get the total results of acres for this polygon that we have. Now we're going to look at the data frame namespace, which is spatial. And this is going to give us those data set level operations. Some of the operations are descriptive. Some of them are actions that occur on the data set as a whole, like projection and spatial joins. Our I/O operations, our read-write operations, also exist on this spatial namespace. So we can visualize our data set as a whole, for example, by just calling spatial.bounding box. This will return an extent, but within Jupyter Notebook, we get that rich, since we have that rich visualization, we'll get back the bounding box and how it looks, though a square isn't very impressive. If you had other geometry type, it would outline the geometry using SVG. We can get the full extent of our data set by doing sdf.spatial.fullExtent. This returns back a tuple starting with xmin, ymin, xmax, ymax. Let's say we want to reproject. So my current data set's in this projection 2240, which is, I believe, a state plane format. And let's say we want to reproject it into 4326, WGS 1984. We just do sdf.spatial.project. This is an in-place method, so it'll update the column to the format that we have. It'll update the existing geometry column, and then we can just requery the spatial reference and see that it comes back as 4326 now, so it reprojected. And now if we look at the full extent, instead of being in that other coordinate, the local coordinate system, it's in WGS 1984, the lat long. The Spatially Enabled DataFrame has its own built-in rich visualization format, and it comes on the method of plot. Just like we saw before with Pandas DataFrame, we were able to graph and charts and do everything like that, but we can make maps out of Spatial Enabled DataFrames as well by taking advantage of the DataFrame's ability to display the map widget that's included with ArcGIS API for Python. The syntax mimics closely to what matplotlib is, so if you're familiar with matplotlib, you'll be able to pick up the syntax fairly quickly. So we use Pythonic syntax, like I said before, and it has the ability also to support multiple renderers. So it isn't just putting points on a map, it's rendering your data the way you need it. And we support out of the box simple, unique with arcade, class breaks, and heat map. And so you can really get your data the way you want. But how do we know how we want to visualize everything? Well, we developed helper functions, and you would just import from ArcGIS.mapping, import show styles and display color maps. So we're going to show styles for the point geometry, pass in the type of geometry we have, in this case point, and returns back the various styles that are supported. We could also change this to polygon as well, or polyline, and we get back the various types. So we have, if you wanted backwards diagonal, you would put in backslash, and that's how it would render those polygons. By default, we have a set of quite a long list of color maps that are supported out of the box, and you could use one of these to fit your needs to render your data, or you could pass in the colors you want yourself. So let's go ahead and connect to our enterprise. And if you don't know, this is how we go ahead and create a map. So I'm going to connect to my ArcGIS Online, and I'm going to use my profile credentials. So I'm going to be a built-in account. And I'm going to do gis.map, set my background to dark gray, and then display the map. And now I have an interactive widget on the map. Let's say we want to get information on there. So I'm going to go and I'm going to pull in a data. This is the World Cities database. It's provided by Esri DM, and I'm going to query it. So we saw before with ingestion that we were when we want to pull in the whole data set, we have these from layer functions. But let's say we want to query it and only take a subset. On any query function on a feature layer, if you set asdf equal to true, you'll get back a spatially enabled data frame. And this will allow you to do subsets. In this case, I'm going to pull down everything, but I could limit my, let's say I only wanted the country of Brazil. I could set country name equal to Brazil. I would get a subset of my feature layer, pull it down, and my spatially enabled data frame, because I set that equal to true, would only contain information for Brazil. But I want the whole world. So here we have the first 5 rows for our data frame. Let's go ahead and pull that in. And now we have our data set. If I didn't have an existing map data frame, I could do df.spatial.plot. And what it does is it'll create a generic map and it'll put everything on there. And it'll choose random. If I don't put anything into the plot function, it'll just pick a random color scheme and put it on the map. In this case, it picked orange with a gray outline. I could then go ahead and let's say we wanted to do some more advanced stuff. So I'm going to create a new map, set it to be over YARP because I'm pulling in the extent from my first map that I was panning around. And we want to plot these points on the map. But I want to make it a little different. I don't want it to just be circles and random. I still want it to be simple, but I want it to be square, so I'm going to use the S symbol. I'm going to choose the color map red underscore R, which is red reverse. I want to take the 10th color within that color map, and then I'm going to say I want my outline color to come from this color map as well, and set the marker size. Let's see how that looks. So we get information here. We see the information on the map, and I'm going to zoom in a little, and we get our squares, and it has an outline value, and then we see that just like we would expect with a feature layer, we can interact with that and see all the information. We can do class break renders. Here's an example of a map. We're just looking at the United States. For each country, we set that's going to be the class break. Here I looked at the columns. I saw that I had the country name here. So I said on map 3, M3, I want a unique renderer, and I want the column name to be country name. And then we get the result. We can do class break renders on numeric columns. So here we're going to take advantage of the JavaScript API and do class break natural breaks algorithm for the classification. I'm going to specify the number of classes, set that numerical column to pop, and provide a color map, as well as an opacity level of 0.7. And here we can see our points with the opacity levels set. So far we've seen mainly just polygons, but we can do it also with points, but we can also do it with polygons. Just taking data that's census information, doing that same natural breaks classification on our column, setting our alpha, and then also our line width, and we get the representation that we want. Besides having the ability to do rendering and all the other functions that we can do with that, we also have what's called on-the-fly spatial indexing. A spatial index, for those of you who know, is just basically grids up your world or your data into points and allows you for fast access of that information easily. So you have the ability. So we're going to pull in the major cities again for the U.S. and we're going to get our data. So we're going to query it as DF. We're going to set our out spatial reference to 4326, and we can see that we have 3,886 layers. I'm going to create an index, and I'm going to use rtree. I'm then going to query it for an intersection, the index. This is going to return back a list of index values for our Spatially Enabled DataFrame. Because we're doing general searches, and they're by bounding box, you notice we don't get the exact geometry. So if I was interested in only the state of New Jersey and finding things, the cities within there, you can see that we're getting Delaware, Pennsylvania, and New York. And so I didn't accomplish what I wanted. So because it's a bounding box, it's a generalization. So let's go ahead and pull some information down, and I'm going to get the New Jersey boundaries. And when we look at the New Jersey boundaries for the shape, we can see that we have the shape of New Jersey as expected, not clipped by the water boundaries. To get the exact extent, what we're going to do here is we're going to use this method called disjoint on our geometries. So we're going to create our subsets of our cities based on the original extent that we had before. Now we have a subset of our data, and we can see, like we saw visually, we not only have New Jersey, we have New York, Pennsylvania, and Delaware. So we're going to take our extent cities.shape.geom and use disjoint, pass in our geometry of New Jersey, and set it equal to false. So this means that we're going to find points that intersect. This is going to give us back a Boolean series. We pass that into our data frame, access the spatial endpoint, and plot it out. And now all our cities shown are within the boundaries of that New Jersey boundary. So spatially enabled data frames have the ability to also be passed into spatial analysis tools. And you can use geoprocessing tools directly with spatial enabled data frames. So we can go ahead and create subsets of data and fire that off quickly to any tool. So in this case, I want to just look at these 4 rows within my table. I'm going to pull them out, and we can see what we have here. So this is some population data on our point data set. You can see the shape XY, lat long WGS19.4. And let's say I want to do a viewshed analysis. So I'm going to bring in this tool, so ArcGIS.create viewshed, pass in my Spatially Enabled DataFrame as a feature collection, set the distance, and go ahead and calculate it off. And notice we get back a feature collection. We can go ahead and do the results and see and add it to the map, and we can show the information on the map. So we just took information, got it back, and then displayed it. So we derived a new product from a Spatially Enabled DataFrame. Another way we can use Spatially Enabled DataFrames is through enrichment. And enrichment is going to allow us to gain insight for a location. So we're going to take that same data set that we had before, and we want to gather some additional information, specifically on age. We want to know the various ages that are within there. So we're going to go ahead and call enrich with our Spatially Enabled DataFrame, the subset data for our 4 locations, bring it in, and we get our population information returned back with the original column names that are on there as well, and we can plot it on the map. The interesting thing to note when we look at this data set is that it turned from a point to a polygon, and that's because GeoEnrichment will convert and buffer points by, I believe it's 1 mile, to gain the average statistics for the point location of where you're going. So just keep that in mind. And we can also use Spatially Enabled DataFrames for custom analysis. We can use things like scikit-learn, Yellowbrick, and and all those other ones, PyTorch, and you can use Spatially Enabled DataFrame to drive that analysis. So here's an example. We're just going to pull in some data. This is listing information for Airbnb. We're going to load it in with CSV. I had to set low memory because it had some wonky data type issues. And I want to examine some review scores. So I'm going to pull out the columns that I need and describe it and get some basic statistics of each one just to give us a general feel. We're going to then go ahead and pull out anything that doesn't have a review score using a simple query, and then spatially enable our data frame by doing from XY. Now that we have that, we can get our full extent, and we can see our study area. We're over Amsterdam. We can use scikit-learn's clustering. In this case, we're going to use k-mean clustering to do this. And we're going to do some, we're going to set some queries. So I want to just look at entire home or apartment for my room type and the number of beds that are greater than 4 to do my analysis on clustering. So we're going to make another subset and then set our rental price, do some cleanup. So now we're doing all those tidy data functions that we had before. We have our method chaining, passing in our query, dropping the NA values, copying and resetting the index, and then we're going to use method chain again to look at price. With the string, we're going to replace the $sign and the commas, and then cast it to a float. And now we can go ahead and we can figure out how many clusters we should have. I'm going to use a package called Yellowbrick, which is going to allow me to easily visualize the elbow, the K elbow, which is going to allow me to know the optimal number of Ks or clusters that should be used for this data set. So it's suggesting 4, so I'll start with 4. Let's go ahead and then we're going to perform our clustering. I'll create our cluster model, do a fit predict, get our classes back, and then visualize it on the map here. So we have our various clusters of how they all cluster together. And this is just a real quick example of how we can take this information and use third-party modules to do our analysis. But now I'm going to look at another way of doing analysis using a combination of both ArcPy and the Spatially Enabled DataFrame. And what we have here in part 4 is we're going to look at access to public transit. And the goal is for the city of Chattanooga, Tennessee to consider adding a new bus route or bus station, and they haven't decided where they need it the most. So how can we use the Spatially Enabled DataFrame coupled with ArcPy to do this? So we're going to go ahead and set up our environment. We're going to import Pandas and ArcPy, and then we're going to import the Python ArcGIS API for Python functions that we need. I'm going to go ahead and I'm going to connect to my GIS, ArcGIS Online, and now we're ready to begin. So I had pulled down data in advance for this GTFS, and this is general transit feed information, and we're going to convert it to a feature class. And luckily for us, this information for all this data can be converted using ArcPy or using Spatially Enabled DataFrames. So I'm going to read the CSV in and just look at the first 10 rows. Notice we have a stop, lat, and long. Next, I'm going to look at another set of data with the stops, and then we're going to do that conversion directly and then write it back out to a feature class. Now that we have that, let's visualize it on the map. We can see we have our point data showing all the current stop locations for the city. And we zoom in out, you can see that there are high concentrations of stops, but let's figure out where we might need more area, more stops to better serve people. So we're going to use some analysis and we're going to create drive time areas. We're going to pass in our Spatially Enabled DataFrame, and because this is a web tool, and this web tool specifically has a limitation of 500 rows per entry, we're going to go ahead and break up our data frame into two groups of 500. So our first one, we're going to do stops and then use that iloc syntax and then get the first 500, cast it to a feature collection, send it in, and we're going to have a 5-minute walk for there. And then we're going to dissolve all the outputs and then do the same thing for the second part of our stops for the 5-minute walk. We're going to go ahead and concatenate these two together using ArcPy. We're then going to dissolve our points together. And then we can go ahead and we can plot this on a map and we can see our drive times for the city as shown. So those are within a 5-minute walk. These are the areas that people can get to from each bus stop. So we need to determine future bus stops, and one way to do this is to grab some census information. We're going to get block group data for our city, and we're going to query out that information, and this is what we have. Notice we're missing our statistical information that we would need. So let's just overlay it so we have a better understanding of what our data looks like for the city. And now we can go ahead and we can enrich this information. We're going to use geo-enrichment like we did before. Pass in our block, Spatial Enabled DataFrame, and then we're going to take the variables that we need. So before we looked at age as a whole, but in this case we're going to take individual variables because we know we only need certain ones. And this information is going to give us, we're going to look specifically at these at-risk values, which is the total population counts, available car data, and the number of families below the poverty line. We're going to look at that information. And then, so once our data is enriched, we can see we get back the information that we need, and we can go ahead and start making some calculations with the bus stop coverage. So we're going to load our drive times back into a Spatially Enabled DataFrame, and we're going to create a spatial index. And we're doing this because we want to limit the extent to just the city of Chattanooga. We're then going to do we're going to take our enriched blocks and we're going to do some calculations. So we're going to get the average population density per square mile. And then we're going to calculate the number of counts for each block that we have stops. And then we're also going to create another new column on the fly where we have the stop count, and then we're going to divide by the population density. So because we want to know the stops per person. Now we're going to remove well-served areas. That's the first thing we're going to do. So let's go ahead and we're going to convert our data back to a feature class, and we're going to take advantage of the ArcPy erase function. So we're going to erase out our drive time areas that are already served, and then load back in our final area where the blocks are. We're then going to go ahead and do an intersect, which is going to give us our indexes. And then we're going to get our final blocks of where the most underserved areas are. We can then take this information using the power of Pandas, set some criteria on the areas that are left that are underserved, pass in our query, copy it out, perform a plot operation, and put it on a map. We can then go ahead and take this information and persist it back to our organization, and it'll allow us to find an area where bus stops should be put first and new routes.